Perseverance just hit the most compelling hint of ancient Martian life, yet a mudstone core called Sapphire Canyon, packed with organics, water-cut veins, and mysterious leopard spots. A peer-reviewed study elevates these as potential biosignatures, the best candidate so far. In this video, we'll unpack what the rover found and how scientists tested life versus geology. Perseverance drilled a slender mudstone core called Sapphire Canyon from an arrow-shaped rock nicknamed Cheyava Falls on the western side of Jezero Crater, where the ancient Neretva Vallis River once flowed into a lake. The target sits within the Bright Angel Formation, fine, water-laid sediments later cut by mineral veins, so it's the kind of archive that can lock in delicate chemical textures for billions of years. The core was taken in July 2024 and later highlighted with new analyses in 2025, drawing attention because multiple independent clues converge in a single slice of rock. Up close, Cheyava Falls is speckled with tiny ringed features, informally called leopard spots, and millimeter-scale nodules nicknamed poppy seeds. Perseverance's arm-mounted instruments mapped these textures and their chemistry. One instrument detected organic compounds embedded in the mudstone matrix. Another produced elemental maps showing that many ring rims are enriched in iron phosphate, Vivianite, while interiors concentrate an iron sulfide, Greigite. Threading across the rock are white veins of calcium sulfate, clear evidence that liquid water migrated through the sediment after it was deposited. Why does this combination matter? Because the collocation of organics with redox-sensitive iron and sulfur minerals inside a water-cut mudstone is exactly the sort of arrangement that, on Earth, often records microbial activity in calm lake sediments. Add in subtle color shifts linked to iron minerals, and you get a plausible chemical energy gradient that life could exploit. None of this, by itself, declares biology. What makes Sapphire Canyon stand out is the stack of consistent indicators, textures, minerals, and organics appearing together in a low-temperature, water-rich environment. The core question is mechanism. Could ordinary geochemistry produce the leopard spot textures and their mineral zoning, or did biology help organize them? Scientists treat this as a competition between two end members. In the abiotic scenario, reactions among iron, phosphorus, sulfur, and simple organics generate Vivianite-trimmed, Greigite core structures during burial and fluid flow. No microbes needed. In the biotic scenario, microbial metabolisms in a shallow lakebed create redox gradients that guide where minerals grow, leaving organics and textures in recognizable patterns. To sort between them, one powerful discriminator is temperature history. Many abiotic processes that mimic biology's patterns rely on later heating to reorganize minerals and overprint textures. In Cheyava Falls, the preserved mineral roster and delicate fabric do not show strong signs of high-temperature alteration. That doesn't prove life. It simply narrows the range of purely chemical explanations to those that work at low temperatures in water-saturated, oxygen-poor conditions. Those are precisely the conditions expected in a calm lake environment with slow fluid circulation. Another check is geologic context. The Bright Angel outcrops sit where a once energetic river system fed into a quieter lake. That river-to-lake transition naturally sets up chemical gradients, layers fine muds, and later allows fluids to thread through the rock, depositing calcium sulfate veins. The head-turning detail is pattern. Organics appear where ring rims and cores show distinct iron phosphate and iron sulfide zoning. On Earth, similar spatial pairings are commonly associated with microbes breathing iron or sulfate as part of their energy cycles. It's the arrangement, not any single molecule, that raises the confidence level. Scientific discipline matters just as much as the data. The interpretation has been advanced carefully as a candidate biosignature rather than a proclamation, explicitly inviting the broader community to replicate these features in laboratories. Turning a candidate into a confirmation almost always requires Earth laboratories. Perseverance has already pushed its toolkit to practical limits at Cheyava Falls. Organics mapped with ultraviolet Raman/fluorescence, elements mapped at fine scale with X-rays, and high-resolution imaging to capture textures and veins. These instruments are superb for triage, finding and prioritizing promising targets. But the decisive tests live in labs on Earth, where scientists can probe nanometer-scale textures, measure isotopic ratios that betray biological fractionation, and identify specific organic compounds far beyond the sensitivity of any flight instrument. That's why Mars sample return is so central. The goal is to deliver sealed cores, including Sapphire Canyon, to curated facilities on Earth. There, teams can run an orchestra of methods: electron microscopy to test whether ring boundaries show growth patterns typical of biological mediation, synchrotron-based spectroscopy to resolve the exact iron and sulfur states, clumped isotope and compound-specific isotope analyses to check whether the organics carry fractionation signatures hard to produce abiotically. This is how the field moves from lifelike to life. In parallel, expect a surge of analog and synthesis experiments. Researchers will mix iron, phosphorus, sulfur, and carbon compounds in cold, oxygen-limited brines, adjust pH and redox, and watch whether Vivianite rims and Greigite cores assemble into Mars-like rings. They'll test how fluid flow and ion diffusion shape those rings, and whether organics naturally concentrate where the rover saw them. If labs can generate indistinguishable textures and chemical maps without microbes, we'll refine a powerful abiotic script. If not, the biological pathway gathers momentum. On Mars, Perseverance still has valuable work, mapping how widespread the Leopard spot textures are across Bright Angel, checking nearby units for the same organics plus iron mineral pairing, and tying textures to specific positions along the river-to-lake transition. That context will matter when cores arrive on Earth, helping scientists judge whether Cheyava Falls is a one-off curiosity or part of a repeatable environmental recipe. In one small core, we see organics, water-cut veins, and iron-rich rings arranged exactly where an ancient lake once breathed with chemistry, an environment that on Earth often records microbial life. It's not a declaration, it's a direction. The next steps are clear: replicate these patterns in labs, expand the contextual mapping on Mars, and bring the Sapphire Canyon sample home for definitive tests. Whatever the verdict, we've zeroed in on the right place, the right minerals, and the right questions, bringing us closer than ever to answering whether life once existed on Mars. If you enjoyed this video, don't forget to like, share, and subscribe, and don't forget to leave a comment below. Thank you for watching. See you next time.